I'm going to briefly go over the color shift and the phases of wood combustion. We use color shift analysis to determine where the fire is or the fuel is during the fire. So that if you drop a piece of wood on the fire, there's first a drying phase. There's going to be some smoke and a little color shift, but it's mainly driving off the moisture at the perimeter or outer surfaces of the wood. After you go through the drying phase, and it's not the whole log, but just the surface, a few millimeters of the surface, then you go into the pyrolysis phase where you have increased smoke production and you may be burning off that smoke, or it may be going out the chimney unburned and come out as smoke. There'll be a noticeable color shift, and you'll get some volatile gases. Sometimes you can burn that off, sometimes you don't. Then you get into the combustion phase where you have intense burning, and I think in the background here we're in the combustion phase, and a distinct color shift from the high particles. So then you get down to the char burning phase where you simply have glowing embers. And in this phase, you have very little opacity and you have a residual color shift that's small. When we use the corrected color shift algorithm, we're seeing a small amount of particles and very low color shift, very low opacity. So the char burning phase does not produce as much particulates. The particulates are extremely fine. We don't see them in the chimney, and all the moisture is essentially at the minimum, so that you don't get a lot of condensation out the chimney. I'm going to explain smoke measurement. So smoke is extremely small particles, and there's a couple different ways to measure it. I've developed one method that is unique in some ways. It's used in laboratories, and I'm using it in my devices. So the importance of measuring smoke is that, one, we can document what's going on inside the stove, and we can make readings to make corrections to make it burn better. And it's important at a 9 or 10 level, 9 out of 10, because it's in line with fire safety, air quality monitoring, and environmental research. So light interacts with particles in different ways, and we can see it when we drive by and see a chimney smoking. Most of what you see is water vapor. However, if you see particles and clouds and eddies traveling some distance from the chimney, you can assume that that is smoke. It's illegal to put out too much smoke, and it's illegal to have the smoke travel onto your neighbor's property and bother your neighbor. If we can measure the amount of blue light that is scattered away from the light beam, we can measure particles as small as the beam of light in the blue range. So 400 nanometers down to 40 nanometers. We can document the size and quantity of those particles within certain confidence intervals. So incident light is how bright a light is. And how bright a light is, when you put two lights together, the human can determine which one is the brighter one. If the light are the same shape and they are the same color, and one is twice as bright as the other, most people can figure out which one that is, which light is the brightest. Digital light sensors can do it. I put a value on those light, the light coming into the sensor. So a human could say one's brighter than another. The digital sensor could say this one is 40 and this one's 20. and this one's 42, and this one's 22. Okay. The other thing I can measure is color shift, and color shift is a measure of the light's color or peak frequency. So white light is a broadband, but it has a peak frequency. It's normally going to be somewhere between 400 and 800 nanometers. 400 is a good blue light. If you use a light that has a balance of blue and other colors, you can determine how much of the blue light has been scattered away and is not being received by the sensor. And that's a color shift toward the red. And we see that as humans when the sun sets on a smoky day, it turns red. That means the blue light has been scattered away. All right. So the practical applications for my method are real-time control of a wood stove. And you can control the wood stove in a couple different ways. In general, it's going to be airflow. You can change airflow nozzles, you can change airflow locations, you can change the quantity of airflow. And you can do that based on a response from an opacity monitor that can measure the color shift. Therefore, we can tune in the best quantity of air. We did some testing. I'm using a blue light. Let me get the blue light out so you can see it. Now, when I look at that, it looks like a blue light. There's a display that's in yellow in the front. However, the light source that's going through the octoring leaks out into the octoring and illuminates it in blue. That looks blue to me. All right. So the data we get from the blue light has some benefits. It's very stable. You see between 15 and 18 hours of baseline. It's just not moving around at all. The temperature is the green line around 50 degrees Fahrenheit. We put a fire in and we get momentary opacity measurements up to 80, but really only for a few minutes. And then we get this color shift, and I've also got a corrected color shift in there. The color shift indicates small particles because it's scattering off the blue light. So we get a rise in color in nanometers, and that's measurable, and we get it in fine detail. So you can see there, I put 3 pieces of wood on, or 3 times I loaded the stove with significant chunks of lumber, and the last one I put a really big log on. So I'll go through some more data here. This is the log I put in there, and it's partially burned at this point. However, this is a problem with wood stoves, is you get a piece of wood in there and it's occupying the space to put more wood in, and you can't get the wood stove to burn it because temperatures are dropping and you've got a big log smoking in your wood stove. Well, my wood stove's kind of tuned in and it burns these things quite well. But you can get an idea what I'm talking about. If it was just all coals in there, I could put another piece of wood in, but with that piece in there, I can't really put much more in. One of my solutions is to put pellets around it. So I'll scoop some pellets in and then close the door, and the pellets help that burn. This is the diode response from the 4 light sensors on the sensor. And you can see it's saying this is a blue light. So blue and clear are reporting in quite high, between 7 and 8,000 at the brightest point. We do have some anomalous readings, but they're very short. And let's see here. They were during high opacity times. So the red and green are just not very prominent in this, and I think it becomes a problem later. This is a normalized light sensor response, and this is useful to determine when the colors diverge. So that you can see blue being stripped off and red and green following together. This is a very blue light, and we see a more prominent red deflection. I'm not sure why that is, but it is present. Green seems to come through the best. Blue next. Clear is right in there, but red seems to be torn off in this one. So I'm bringing in my rate of rise chart. Now the rate of rise chart tells me, one, we had a very good startup on this test. We got up to 20 degrees per minute of rate of rise. After that, it drops down and crosses 0 at about a half hour. So that we put another piece of fuel on, and we get another rate of rise that goes up to 15. The key thing about the rate of rise chart is you can tell when the wood stove is starting to cool down. And it's still hot. However, using math, we can inform the operator we're getting close to the time where we need to plan to put fuel on. And putting fuel on the fire at the right time is a key parameter in reducing smoke production. This is my fan control. You can see I'm sending spikes of voltage to the fan to speed it up and let it spin down. This has been what I found to be the best way to control fire in a wood stove. One, you already have to have a draft established, and so we're simply pushing the flame from one side to the other to it just works better for cleaner burning. And this is what the graph looks like. It looks like the fan is speeding up and slowing down.